Welcome to the Unit 12 Mixtures and Solutions video notes. A little bit of review classifying matter. So matter can be broken down into either pure substances, which can further be broken down into elements. Here we have a simple monatomic element, so think of helium or neon or potentially even an element like carbon or gold. These atoms can be found individually. Over here, even though they're in a compound, it's still an element because all you see is the same atom. The fact that they're in pairs, 2 per group, I would think that this probably suggests we have a diatomic, like oxygen or nitrogen or hydrogen. But either way, all we have is just that element, so this is an elemental substance. Pure substances could also be compounds. Now, as long as we have the same compound, even though we notice we have an orange molecule in the middle and 3 yellows going around the outside. So we have different elements here, but they're always in that 3-to-1 ratio. So it's always the same compound, and we have nothing but that compound. So this is also a pure substance. On the other side, matter can also be mixtures, and that's going to be the focus of this unit. Mixtures can be further divided into homogeneous or heterogeneous. Sometimes you might hear them homogeneous or heterogeneous. How you pronounce them, it's fine either way. Now, the easy definition to distinguish between homogeneous and heterogeneous is that homogeneous is mixed evenly, whereas heterogeneous is not mixed evenly. But that's not always the best definition. In a homogeneous mixture, you can't see the distinct parts. Think of a saltwater solution. You can't see the salt mixed in with the water. In a heterogeneous mixture, you have visibly distinct parts, and you can see them. Think of a salad. A salad could be mixed evenly, but you can still see the distinct parts. You can see the leaf of lettuce, the slice of tomato, the piece of cheese. So a salad would be a heterogeneous or heterogeneous mixture, even though it is still perhaps mixed evenly. A word we use to refer to homogeneous mixtures is solution. So these 2 words are similes. We'll use them all the time. Interchangeably, a solution is a homogeneous mixture. A homogeneous mixture or solution, they are the same. Heterogeneous mixtures can be further divided into colloids and suspensions. And that's what our next slide will cover, the difference between colloids and suspensions. So looking at just our heterogeneous mixtures. Oftentimes it's easy to say that we have a heterogeneous mixture. Think about dirt in water. Even though you might shake it up and it might be dirty water for a few minutes, eventually that dirt is going to settle out. Other heterogeneous mixtures are a little bit more difficult to tell that they are heterogeneous indeed, because their particles are still pretty small and they may not settle out in the bottom. Leave it to scientists to come out with a very exact definition, and sure enough, they have. Solutions technically have particles that are smaller than 10 to the negative 7th centimeters in size. That's incredibly small. That is 1/10 of a micrometer. So that's very, very, very small. Colloids are a little bit bigger, so between 10 to the 7th centimeters and 10 to the 5th centimeters, we have colloids. Particles are in that size range, and oftentimes it may not necessarily be a larger atom. It could be, I suppose, but not necessarily a larger atom, but an atom or a group of atoms that doesn't completely dissolve, which you see here in the image of a colloid. And finally, you get to a suspension, which are going to be very large particles, greater in size than 10 to the negative 5th centimeters. So you can almost see these with the naked eye. Here's a large cluster of individual atoms and ions that are not dissolved, and they would make up a suspension. So again, colloids are your intermediate size. They're larger than the particles of a solution, but smaller than the particles in a suspension. Some examples would be Jell-O, Gatorade, even fog, like you have in the morning sometimes. Mixtures don't have to be a solid and a liquid. They could be two liquids or two solids for that matter. Suspensions then are the largest particles mixed into a liquid solution, or it doesn't necessarily have to be a liquid solution. They usually contain an instruction such as mix well before use. An example would be flour in water, like baking flour. You put that in water and you can kind of picture that. It's almost a Play-Doh-like structure. It can drip through your fingers. You can mold it into a different shape. That is a suspension. Mud or muddy water is also an example of a suspension. Typically, a suspension by definition won't settle out. So if that muddy water settles to the bottom, or if that dirt settles to the bottom, I don't know that it would be classified technically as a suspension. Long story short, don't memorize the numbers. I've got them up here because, yes, chemists do like to be exact, but I'm never going to give you a particle and give you its size and say, based on its size, what type of mixture do you have? Don't worry about these numbers. They're just to show that solutions are the smallest, colloids are the intermediate size, and suspensions are the largest sized particles. So sometimes it's difficult to see the actual size of the particle in the solution. So a way to tell if you have a solution, a colloid or suspension, is to shine a light through the mixture. This is called the Tyndall effect. When the light travels through a solution, the light is not broken up by any of the particles. It travels straight through, and in the image here, you cannot see the beam of light. None of those particles get diffracted back towards our eyes. You can see that in the image over here with the laser beam in the water. And the laser beam is going straight through this first glass of water. Probably implies that you're working with a solution. You don't see the laser in the water because it's traveling straight through. None of those particles are large enough to diffract the light into different directions. Light will also pass through colloids, but it gets scattered by the particles in the colloids. So you're going to end up seeing the beam of light. Again, there's the laser, and you can see it clearly in this glass. That beam of light is going through. You can see it from the side as well. This glass, even though without the laser, these two glasses of water may look the same, the glass on the left contains larger particles because we have the Tyndall effect on display. We can see that light as it travels through. Suspensions will generally block the light altogether. The light will not go through. It'll get broken up. It might illuminate the mixture itself, but it won't go through. So if we were to add a white piece of paper, see if we can do that here. If we were to add a white sheet of paper back on this side, that laser beam is still going to travel through our colloid. So we've got our paper there, we'll change colors of pen. Now I've got our laser. That laser is going to continue, and you would see that laser, it would make a beam, it would make a dot on that white piece of paper. If we were to add a suspension, getting to work with my art skills here, that laser would probably not be making it all the way through our solution. Again, it might illuminate this suspension, it might illuminate this suspension. You might see a big red blob here, but we would not expect to see that red dot get all the way through and onto the white piece of paper. It's going to get blocked by that suspension. Here's a link to a very interesting article. If you've ever wondered why eyes have different colors, this article explains at least why we have blue eyes. The Tyndall effect at work. Blue eyes are actually the same process that's going on in the sky. Why is the sky blue? So take a read if you're interested. A little back knowledge on the Tyndall effect. We're going to go ahead and move on though. Most of this chapter will be working with solutions. Most of the time in chemistry, we mix salts into water, they dissolve, and we can then run reactions by mixing one solution with another. Solutions are comprised of a solvent, which is almost always water. Water is known as the universal solvent. It's one of the few naturally occurring liquids. If you think about it, most other liquids are a mixture in water. So it's an excellent solvent. It does the dissolving. It has the solute particles within it. So here's an image. We have the solute, which is dissolved in the solvent. Together, they make the solution. When two solutes mix together evenly, they're said to be soluble. You guys have already worked with these on your solubility rules. When we did reaction types, we looked at did certain ionic compounds dissolve in water, and if they did, we called them soluble. A solute that will not dissolve in water, will not mix with the water, is said to be insoluble. So again, when we did reaction types, we would call our insoluble salts solids. They did not mix with the water, they're not aqueous, they're insoluble. If you're working with two liquids, so again, mixtures do not have to be a solid and a liquid. You can dissolve one liquid into another. Liquids that mix readily are called miscible. And two liquids that do not mix are said to be immiscible. And we have the image here. Acetone and water is miscible. You do not see different layers. Those two liquids have mixed equally. If you've ever added oil to water, or the picture here has water and methylene, you'll notice that they are immiscible. We have a top layer and a bottom layer. It's very easy to see that those two liquids are not mixing. Even if I were to shake that test tube up, and yes, maybe I could get them to mix for a minute or two, they wouldn't stay mixed. They would settle out. They're immiscible. And oftentimes that has to do with the polarity or lack of polarity that the substances have. So the reason that water is our universal solvent is its polarity. It's an incredibly strong dipole. Those hydrogen bonds, again, you can notice if you look closely, we've got the delta positive down on the H's side and the delta negative on the oxygen side. When we put salts into water, those delta negative sides are going to be attracted to the positive, the cation. And again, we can see that here. Here is a sodium ion that has been pulled apart by those negatively charged or partially negatively charged oxygens. And the anion, in this case chlorine, is going to be pulled apart by those positively charged or partially positively charged hydrogens. So those dipoles are everything. This is how salts dissolve, and this is why here would be a big chunk of white salt. We'd see that crystal, what you're looking at here, and we throw that into water. The water pulls apart each individual ion, and these ions are far too small for us to see with our naked eye, and so it looks to us as though the salt has disappeared in the water. We know, of course, there's no magic, things don't just disappear. We know that the salt has dissolved, and this is what it physically looks like. There are three ways to increase the rate of solvation, how fast the molecules or the ions will dissolve. The first way is to agitate your solution, stirring. If you stir, you increase the number of times that those water molecules are going to come in contact with the salt particles, and so you will increase how quickly those water molecules can pull apart those salt molecules. The second way is to decrease your solute size. You can increase how fast it will dissolve by decreasing the size. Perhaps you remember from biology, the reason why cells do not grow infinitely large is because of their surface area to volume ratio. So if you make a particle smaller and smaller and smaller, you're going to get a greater surface area and a smaller volume, and that makes for more interactions with the water molecules. Again, if you think about it, these chloride ions and sodium ions here in the back, they don't get pulled apart until the ones in front of them get pulled apart. They don't have interaction with water molecule until the water gets to them. So if we were to have a smaller chunk of this salt, we would have faster and faster, we could get to the middle and pull apart the entire piece of salt. So the sample size will also increase how quickly your solute is dissolving. And finally, the last thing you can do if you want to dissolve some sugar into your tea a little bit faster is the temperature. The faster these water molecules are moving, that'd be a higher temperature. The faster they're moving, the more collisions they can make with those sodium and chloride ions, and the more collisions they're making, the faster they're going to pull those ions apart. All right, even stirring constantly or continuously decreasing the size of your salt cube or making a very, very, very hot temperature, there's only so much salt you can dissolve in a given amount of water. Eventually, we dissolve so much salt, whatever salt is. In this case, we're actually looking at literally table salt, so the real salt, if you will. Though in chemistry, we generally call all ionic compound salts, or many ionic compound salts. Eventually, our solvent, or water, is going to reach a maximum value of salt particles that it can contain. And at this point, we call our solution saturated, which is a Greek word that means full. Until you reach that point, we say that our water, our solution, is unsaturated or not full. Once you reach that saturation point, doesn't matter how much you stir, or it doesn't matter how small those particles are. Actually, heating can change things. We'll talk in a minute about heating, but additional particles added to your solution at this point, once you're saturated, are just going to fall to the bottom and remain solid. They will not dissolve. And that brings us to solubility curves. For the most part, as you warm up water, so here's our temperature scale on the bottom. Notice it only goes from 0 to 100 degrees. Think about what happens when you go below 0 degrees Celsius or above 100 degrees Celsius. But here are different salts at different temperatures. Again, here's sodium chloride, this relatively stable light blue line right in the middle. And this shows us the amount of salt that can be dissolved in 100 grams of water at various temperatures. So at room temperature, roughly room temperature, it'd be right in here, follow this up, we would expect to be able to dissolve about 35 grams of sodium chloride in 100 grams or 100 milliliters of water. If we want to dissolve more, we can generally warm the water up. So if we brought the water up to its boiling point at 100 degrees Celsius, now we could dissolve about 40 grams of sodium chloride, a little bit more than the 35 at room temperature. So generally, increasing the temperature can not only increase the rate the salt dissolves, but you can actually change how much salt will dissolve. Now there's a lot of different salts listed here, and this is a nice picture because it has color as well, makes it a lot easier to follow. Use this one when you do your homework. Refer back to this graph when you do your homework. Most salts, you'll notice, increase with temperature. cesium sulfate here decreases with temperature. I'm not exactly sure what the reason cesium sulfate decreases is, but I do know that oftentimes when you see this decrease in temperature, the reason is you're not working with an ionic compound, you're working with a molecular compound, which is generally a gas. And think about it, you can dissolve gases in water just like you can dissolve a solid in water. Ever opened a can of pop and go the fizzles? Well, that's a gas that was dissolved in that water. That was carbonation that was dissolved in that water. In a few chapters, or a few lessons, excuse me, this chapter, but in a few lessons, we will learn about Henry's law, which states that as temperature increases, generally gases' solubility decreases. So generally you see that downward curve, you should think you're working with the gas. Most salts increase solubility with an increase in temperature. Hey, watch your volume of water. These charts usually give you 100 grams, or again, 1 gram, 1 milliliter for water. So 100 grams or 100 milliliters of water. Questions don't always give you that. Sometimes we might ask how much salt could you dissolve in 200 grams of water or 200 milliliters. So watch your volume of water and always make sure to double or halve or do whatever multiplication or division step you have to do to figure out the amount of water you're working with. Example question: how much sodium chloride can be dissolved in 100 grams of H2O at 30 degrees Celsius? Here's our 30 degrees Celsius. We follow it up. Boom. Feel free to put a dot on there if you want. Follow it over. And I'm guessing right there between 30 and 40. We know the tens spot. So that means we're always supposed to guess. That shows the accuracy of our instrumentation. We're always supposed to guess one more. We're guessing the ones spot. So 35 grams, appropriate significant digits. This brings us to supersaturated solutions. Perhaps you've heard of them. Perhaps you've even worked with them. And perhaps you even worked with them without knowing you were working with them. Once you reach the saturation point, so going back, if we were to take 30-degree water, 100 grams of 30-degree water, and add more than 35 grams of salt, you're not really doing anything. You would have 35 grams dissolved and 5 extra grams just sitting at the bottom if you went up to 40 grams of NaCl. In order to get a supersaturated solution, you would need to get those extra 5 grams dissolved into the water. That they're sitting on the bottom does not mean you have a supersaturated solution. But if you can get those extra 5 grams dissolved, so if you can get 40 grams of table salt, dissolved in 100 grams of water at 30 degrees, you would have what's called a supersaturated or above saturated solution. Now again, making a supersaturated solution is not as easy as it sounds. You can't just add 40 grams of salt to 100 grams of water at 30 degrees. 5 of those grams would just fall right out. There are 2 ways you can go about doing it. First, you can warm the water up. So if I wanted to dissolve 40 grams of sodium chloride into 100 grams of water, I could bring my water temperature up to 100 degrees. Now it'll dissolve 40 grams. If I then allow that temperature to cool back down to 30, those extra 5 grams should still be dissolved in the liquid. And I would now have a supersaturated solution. Another technique you could use is to allow the water to evaporate. So you won't have your 100 grams of water, but you would have more salt dissolved in less water than what that water is supposed to be able to hold. So again, looking back at our image here, at 100 grams of water at 30 degrees can hold 35 grams of salt. So if I dissolve my 35 grams of salt, but then leave my solution out in the sun and let, say, 50 grams, half of my water evaporate, oh, well, now I'm going to have 35 grams of salt at 30-degree water, but only 50 grams of water. I'd have twice as much salt dissolved as what I should be able to dissolve. That would be a supersaturated solution. I've got a cool link to a cool video where a teacher makes, not me, a cooler teacher than I am. A cool teacher makes a supersaturated solution, and it's cool to see. Perhaps you've already done this. If you ever made rock candy or crystals as a kid, that's the technique you're making. You create a supersaturated solution, you continue to add salt, you let the salt dissolve, and then you let the water evaporate. As the water evaporates, the salt slowly crystallizes, and that's how you make crystals. If you haven't seen my hand warmers before, you should ask me to see them. Those are examples of a supersaturated solution. And that's a real world practical example. Somebody's made a lot of money off of it's a very basic understanding of chemistry. In a couple of chapters, we'll talk about where the heat comes from, where that energy, when you push those hand warmers, when you push that button, we'll talk about where that heat comes from and understand that a little bit better. But that's all you have for day one notes. A little longer than I like them to be. I'm sorry about that. Hopefully you played me on fast forward. I bet my voice sounds better on that. You have homework tonight. Here it is. 8 questions. Take a look. We'll see you guys over the weekend on Monday. We'll check this homework.